Hey guys, Miss Pipel here. We're going to go ahead and go through the remainder of the class material in videos like this. So we're going to first talk about equilibrium, and then we're going to move on to talk about Le Chatelier's principle in a second video. So to go ahead and start with equilibrium, we've already talked about that in terms of thermal equilibrium, if you guys remember. We talked about that when we were talking about calorimetry and heat transfer, but we can really have any type of equilibrium. So that's equilibrium in a simple form is when we have two opposing processes, so opposites, occurring at the same rate. So we can think about a couple different examples that we've seen in our everyday life. So the first one is a fountain. So in a fountain, we have our water coming out of the fountain, right, falling into the pool. Okay, and somewhere underneath there's a mechanism that also pulls that water back into the fountain so that it can continue that process, right? So the two opposing processes would be the water flowing into the pool and the water being taken out of the pool. Okay, we can tell this is at equilibrium because there doesn't appear to be any type of change happening, right? We don't ever see the level of the water changing. It stays pretty much at the same height. It doesn't appear to be moving up or down. But they are opposing processes, water going into the pool, water being taken out of the fountain pool. So that would be a process at equilibrium. Okay, another process or something that we see in our everyday life would be a grocery store or really any type of store, but I think a grocery store illustrates this best. I'm really struggling with my spelling here today, snow day mode, sorry. So in a grocery store, right, we generally have the shelves completely stocked, and the idea for the owner is to stock the shelves at the same rate things are being purchased. So at the same rate things are being taken off the shelves, things should be ideally being put back on the shelf. So that would also be an equilibrium. Okay, so we can apply this to chemical reactions, and we apply this because we generally think about chemical reactions going forward, okay, and the reactants turning into the products. However, we also see it going backwards. So we can have a reversible reaction, and most reactions are technically reversible, although we don't necessarily see that process happening as clearly. So in a chemical equilibrium, what happens is the process of going in the forward direction compared to going in the reverse reaction direction are happening at the same rate. And we can tell that's happening because the concentration or the amount of products and reactants we have no longer appear to change. Okay, that's how we can kind of tell that the reaction has reached a chemical equilibrium. So looking at this on a graph, okay, the rate of the forward reactions and the reverse reactions are the same. So if you look at this reaction of hydrogen plus iodine turning into hydrogen iodide, okay, or hydroiodic acid, there's some naming review for you. We start out with all the reactants. We start with mainly our reactants, and we make the products at first. We go in the forward direction, but eventually, okay, the more products we make, the more that's going to break down and turn back into the reactants. Okay, and the rate of the forward reaction will slow down, the rate of the reverse reaction will speed up, and we eventually meet at this equilibrium state where the forward and the reverse reaction happen at the same rate. Okay, this is just rate. Okay, the y-axis is rate. It's not concentration. We don't necessarily have equal concentrations of our products and our reactants, but the rate at which those reactions are happening is equal. Okay, and we'll talk about how we can use the products and the reactant concentrations to describe this a little bit more. But the moral of the story is that the forward and the reverse reaction happen at the same rate when we are in equilibrium. Okay, so we can quantify this and refer to how much of our products and reactants we have, okay, when we are at equilibrium, right? Some reactions we know go mainly in the forward direction and only will slightly go in the reverse, okay? And we can figure out using this constant, okay, KEQ, a constant referring to equilibrium, that will tell us if at equilibrium we have more products or if we have more reactants, okay? Or we refer to that as being favored, if products or reactants are favored. Okay, this can be dependent on temperature because generally we know that temperature is average kinetic energy. The more energy something has, we might see things going a little faster or being more productive in one way. So this is a constant that is for, it's unique to reactions, okay, and it's dependent on temperature. Okay, so let's see how we can calculate this value. It's pretty simple. So our formula is really products, okay, over reactants. And we're going to refer to this as the concentration. Okay, remember that those brackets mean concentrations. And then we actually use, and you can't really see it on this slide, but we use the coefficients from the balanced chemical equation, okay, as exponents in this equation. So I'm going to rewrite this. So our reaction above, okay, we're going to use the concentration of our products raised to their coefficient, okay, and everything is multiplied here. So then we have our concentration of our other product, D, raised to the power of its coefficient, and we divide our products by the concentration of the reactants. Okay, what you guys are going to be responsible for knowing in here is how to set this up and being able to calculate it given the equilibrium concentrations, okay, plugging things in and making sure we have accounted for everything. Now, the brackets mean concentration, okay? Concentration is generally like amount in a certain amount of space, right? How much we have packed into a certain amount of space. So that's only going to be when we have gases and aqueous, okay? We can only plug in things that are gaseous and aqueous because those are only things that have varying concentration. So if you have a liquid or a pure solid listed in the equation, that does not need to be included in your equilibrium constant expression. Okay, so this really tell us. So if our KEQ is equal to products divided by reactants, okay, we can tell which of those there are more of when we are at equilibrium. Okay, so if we have a situation, a reaction, where it goes really far forward, we have a ton of products over just a tiny bit of reactants left over, okay, that value, right, a number that is large on top, okay, over a small number is going to be greater than 1. Okay, so what that means then is our products are favored. We have more products than reactants when we are at equilibrium. Okay, the forward and reverse reaction rates are the same, but we have produced more products than we have reactants left over. The opposite is also true. Okay, if we have something with not a lot of products, but a ton of reactants, the reaction hardly appeared to go forward. Okay, it has reached equilibrium and we have most of our reactants left over. Okay, mathematically, this is going to turn out to be less than 1, and that describes to us, okay, that our reactants are favored. We have more reactants than we have products. Okay, and then if KEQ is equal to 1, we have an equal mix of reactants and products, right? Something over itself is going to be 1, so they have to be equal numbers. So I'll try and make these as equal size as possible. Okay, that's going to be 1, and that would mean we are right in the middle, equal mix of products and reactants when we are at equilibrium. Okay, so let's go ahead and apply this. So I have a reaction, okay, verbally described here. Water decomposes, so a decomposition reaction, okay, decomposes into its reactants of hydrogen and oxygen. Okay, so I'm going to go ahead and write the states here. Okay, if we want to, we could write the equilibrium expression. I'll do that just so you guys can see that. So we have products. Oh, I got to balance the reaction first, though, so let's go ahead and do that. Here we go. So our products, H2 raised to the power of its coefficient, 2, times O2 raised to the power of its coefficient, which would be 1. Okay, and then we don't have any reactants here because this is a liquid. Okay, so that would be it. We wouldn't have anything on the bottom, so we're really only going to have something on the top. But if we think about this, okay, at room temperature, so in the room you are sitting in, would your water in your water bottle and the glass beside you, is that actively decomposing into hydrogen and oxygen? Okay, not very likely, right? This is likely going to stay to the left, okay? Our reactants, the water are more favored at this temperature, right? Our equilibrium constant depends. Got ahead of myself there. Okay, at this temperature, we have our reactants more favored. It's more likely that it's going to stay as liquid water than it is to break down into hydrogen and oxygen gas. Okay, so our equilibrium constant at this temperature is likely going to be less than 1. Okay, letter C. It's likely going to be less than 1. So that makes sense too, because these concentrations are going to be really small. We can think about those concentrations as being much smaller than 1, so that would give us an actual value of less than 1. Okay, so in your homework, okay, you'll need to set up these equilibrium expressions with your products over reactants, okay, including the proper species in there depending on their state of matter, and then tell me if the value is greater than 1, that means your products are favored. If the value is less than 1, then your reactants are favored. Okay, and that's going to be something you should be able to tell even from a situation like this that we just described. All right, guys, go ahead and look at the Le Chatelier video. We'll go over any questions you have about this when we return to school, hopefully on Wednesday. Stay warm.